Welcome back to the second part of the Introduction to Electricity. This is primarily geared for physics and engineering students. Let's start out with Ohm's law. Ohm's law is fundamental to understanding electricity in simple circuits. We have current in a resistor varies in direct proportion to the voltage applied. In other words, the bigger the voltage, the bigger the current. Right? The voltage is it's electromotive force. It's forcing those electrons to be in motion, and therefore you're going to have more current. But it's inversely proportional to the resistor's value. So the resistor is resisting. That's what resistors do, right? So they're resisting the current and not letting it flow. Bigger resistor, less current. You might be thinking, well, phew, that's horrible. Let's have little resistors all the time. No, not so fast. Some things can't handle. Some of your components can't handle a big current. So you want a resistor in there to lower the current. Maybe you want to save voltage. Maybe you want to save your battery. You want your battery to last a longer period of time. So you want to reduce the amount of current. So let's take a look at Ohm's law. How does this come about? Well, here we have V equals IR. That's the way I usually like to think about Ohm's law. The voltage equals the current. I is a symbol for current, or the abbreviation, and R being the symbol for resistance. So we have the current times the resistance equals voltage. Nice, simple equation. Now we can rearrange that equation so it looks something like our definition up above. Current equals voltage divided by resistance. And the other way to rearrange this, of course, is what if you wanted to solve for the resistance? You have a certain voltage, you have a certain current that you either have or desire. What's the proper resistor to make that happen? Well, the resistance is equal to the voltage divided by the current. And this isn't that hard an equation. It's not very difficult to apply, but you might be thinking, how am I going to remember this? Well, I do have a little device, not a device you carry in your pocket, but a memory device that might help you decide what is the proper form of this equation to solve problems. And that's this little guy. Sometimes it's a circle, sometimes it's a triangle, but you notice we have the V on top, the I, and the R down below on the left and on the right. So what's up with this? Well, if you use your finger and you cover up one of these, let's say you want to solve for V. So let's cover V up with our thumb. There we go. What are we left with? We're left with I and R. What are we going to do with I and R? How about multiply them? So if you multiply those two together, you're going to get V. V equals IR. Not bad. Let's see if we can apply this in other situations. What if we want to solve for the current? Now what are we going to do? What happens if we cover up the I with our thumb? Well, now you have a V over an R. Looks kind of like division. So if you divide V by R, you get the current. V over R equals I. Well, is this going to work for resistance also? Yeah, yes it will. Let's move our hand all the way over. There we go. And we've covered up R, so now we can solve for it with V divided by I. So we're going to divide V by I, or take our voltage, divide it by the current, and that's going to tell us what the resistance is. Great. So we have a little device here that's going to help us solve these problems. Let's do a problem, right? This is a great opportunity now to do an example. So here we have a little flashlight, uses a 6-volt battery, has a bulb with a resistance of 150 ohms. When the flashlight is on, how much current will be drawn by the battery? Let's take a look at what this circuit looks like. We got a 6-volt battery, and we got 150 ohms of resistance. And we're going to show that the current flows from the positive and back to the negative. So we cover up the current, and so it must be voltage divided by resistance. So go ahead and solve this problem and tell me what is the current. All right, very good. So you take your equation, I equals V over R, and we take 6 volts divided by 150 ohms, and we get 0.04 amps. Which is the equivalent of 40 milliamps. Amps is not normally a very large number. As you can see here, resistances can be pretty big, and voltages not that big. So it's not common to have a very low current. A lot of components can't handle a large current. They get very, very warm when currents are very large. So let's talk about circuit configuration. This is the next thing. Now that we understand Ohm's law, There's two different basic kinds of circuits that we can apply Ohm's law in. And one is series circuits. In a series circuit, we go end to end to end with all of our components. What do I mean by components? Well, what about the speakers in your speaker system? What about resistors, light bulbs, batteries, capacitors, diodes, so on and so forth? Any of these and many more could be the components in your circuit. So we could wire them up end to end to end, and then we would have a series circuit. There's only one path for the current to flow. The current doesn't have a choice here. On the other hand, we have a parallel circuit. In a parallel circuit, the current has lots of choices to flow through any one of the different branches. And if you remove a branch, it can flow through the other branches. It's good. All right? So the current's going to keep flowing on this kind. You might be thinking, this is the kind where the light bulbs, you take one out, still works. All right, we're going to talk about that later. And now we have Kirchhoff's laws, and we're going to apply the voltage law to series circuits, and we're going to apply the current law to parallel circuits. So Kirchhoff's voltage law talks about the sum of all the voltage drops in a series circuit equals the total applied voltage. You might be wondering, okay, what's going on with these voltage drops? What does that mean? Well, we're going to see that every single one of the components in our circuit has a little bit of resistance. And if it has some resistance and has a current, well, then that's going to affect the voltage for that component. So we're going to be applying that in just a minute. Secondly, we have the current law. The total current in a parallel circuit equals the sum of the individual branch currents. Okay, we'll do an example of that so you can see how that works. So here we have our series circuit. I was just talking about removing a lamp. All right, this only has one path for the current to flow. It flows out of the positive, through the lamps, back to the negative. If we remove one of these lamps, what's going to happen? Well, it's got nowhere to go. The current can't flow. We have an open circuit and no light whatsoever. So let's take a look at a series circuit so we can understand some of the characteristics of a series circuit. First off, let's talk about the total resistance. The total resistance of the entire circuit is equal to all of the individual resistances added up. We add up all those resistors together and we get the total resistance. All right, very good. What about voltage? Well, we saw from Kirchhoff's law that the total voltage is the sum of all the individual voltage drops. So here we have 12 volts. Each one of these components is not going to experience 12 volts. They're going to experience some fraction of those 12 volts. So here's one fraction, another fraction of the 12 volts, another fraction of the 12 volts, and those three fractions are going to add up to 12 volts. If all these resistors were exactly the same, then we would just take 12 and divide it by 3. And that would be pretty simple. It'd be 4 volts, 4 volts, 4 volts. But they're not. Each one of these is a different resistor, so you need to apply Ohm's law individually to each one of these components, and you can solve for the voltage. Or you can get your multimeter and measure the voltage drop. So let's do an example. We want to find out what the total resistance is. We want to solve for the current flowing through each component. Then we also want to know the voltage across each component, and then we want to use the results to verify Kirchhoff's voltage law. You might think, wow, that is a lot of work. Well, how many equations are we going to need? Basically, just Ohm's law. You'll see. So let's start with the total resistance. We don't even need Ohm's law yet. We just need addition. Go ahead and solve for the total resistance. So the equation we need, of course, is just adding all the resistors together. R1, R2, R3 added together, and we get our total resistance. 220, 470 ohms, 1.2 thousand ohms, or kilo ohms. And we get 1900 ohms, or 1.9 kilo ohms. So there's our total resistance. So what about the current through each component? Why don't you go ahead and try and solve that? The total current is equal to the total voltage divided by the total resistance. We just solved for the total resistance. We were given the total voltage, right? 12 volts. So therefore we know voltage divided by resistance is going to give us the current. and that's going to give us 6.3 milliamps. Again, small number. 12 volts divided by 1.89 kiloohms. Really big number, you're going to get a small number. This is a series circuit. Because it's a series circuit, every one of these components is experiencing the exact same current. So what does that mean? Well, the current here through the battery is the same current as this component, and this component. There's nowhere else for the current to go. So it's the same current everywhere in this circuit. What about the voltage across each component? We're going to apply Ohm's law to every one of these components, and we'll find out what that voltage is. So here's R1, R2, R3. So we're going to solve for voltage 1, voltage 2, and voltage 3. Go ahead and try and solve for those and see if you get the same answer. Voltage 1 is 6.349 milliamps times 220 ohms, or 1.397 boom, 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 volts. What about voltage 2? All right, same equation, but you apply it in case 2. 6.349 milliamps, same current, right? We have the same current everywhere in this circuit, times the 470 ohms, and we get 2.984 volts. Then we apply the Ohm's law to the third voltage drop, V3, the voltage drop across resistor 3, and we get 7.619 volts. So let's see. When we had a small resistor, we had a small voltage drop. Bigger resistor, bigger voltage drop. The biggest resistor in our circuit produced the largest voltage drop. So it takes a lot more volts to move this current through this larger resistor. Okay, so does this verify Kirchhoff's law though? That's what you're wondering. This whole time you've been on the edge of your seat wondering, is this going to verify Kirchhoff's law? Let's find out. If we take all three of those voltage drops, add them together, do we get the total voltage? Do we get 12 volts? The 1.397 that we had going across R1, the 2.984 volts that we had going across R2, and the 7.619 volts that we had going across resistor 3 added together equals 12 volts. Whew! Kirchhoff is really happy that we verified his law. I'm sure he feels very relieved. All right, so 12 volts, we're good to go. All right, let's take a look at parallel circuits. This circuit has, of course, more than one pathway, like we said before. If we remove a light bulb, the other light bulb keeps shining. It doesn't really matter because the current still has a path to follow. Let's talk about the characteristics of a parallel circuit. Things are a little bit different here. So the voltage across all these parallel components is the same. The same voltage is experienced everywhere. So 15 volts here, 15 volts here, 15 volts here, 15 volts here. They're all going to experience the same voltage. What about the resistance? Well, it's a little bit trickier. You take R1 and you take the inverse of that. Add R2, inverse of that, R3, inverse of that. Get the total, take the inverse of that. That is the way to solve for the total resistance of this circuit. See, what's going to happen is, because there's all these pathways to flow through, the total resistance of this is less than any one of these components. So you can see that 470 ohms is our smallest resistor. Well, the total resistance is actually going to be less than the 470 ohms. Now, each one of these branches has a different resistor, so they're each going to experience a different current. You can apply Ohm's law to all three of these. Because the voltage is the same in all three of these branches, but the resistance is different, the current is also going to be different. But all these currents added together are going to be equal to the current that was traveling across this battery, or I total. Let's go ahead and solve for the total resistance of our circuit. We're going to solve for the voltage across each component of our circuit. We're going to look at the current flowing through each component, and we're going to use these results to verify Kirchhoff's current law. Whew, that's a lot. But you saw that actually it wasn't so bad for series, and it's not too bad for parallel circuits either. So let's start with the total resistance. I actually have a separate video on the Robot Readinger YouTube channel. It's very short and deals with how to calculate total resistance easily using your calculator. So at this point, you might want to take a look at that. Let's go ahead and solve for the total resistance. The total resistance is equal to the inverse of the sum of the inverses of R1, R2, and R3. Well, what does that mean? So we have the inverse of 470, the inverse of 2.2, the inverse of 3.3, 1,000 ohms. And it was the 2.2 was also 1,000 ohms. You take the inverse of each one of those, and then you take the inverse again, and you get the total. So that's also covered in that little video I was just talking about. That comes out to 350 ohms. So you can see 350 ohms is less than any one of these three because it's easier, right? You have this much resistance, and this much resistance, and the current has all these pathways to cover. So even though you may have, this could be a major thoroughfare, right? This is the 405 freeway. It's 8 lanes, 4 in each direction. And then you have these little narrow bridges slowing things down. But because you have 3 of them, it's not so bad. So even though only a few cars can get over this narrow bridge, some of the cars can go over this bridge or this bridge, and in the end, you'll have more cars getting through. Little parallel for you. Get it? Parallel? Oh, I think we better move on. The voltage across each component is the next thing. Well, we already know that. They're all the same. Every one of these components has 15 volts because it's a parallel circuit. So what about the current through each component? Well, now you're going to have to apply Ohm's law to each one of these branches. So that's the next step. Apply Ohm's law to each one of these 3 branches, knowing that we have 15 volts and we have these 3 values for resistors. 470, 2.2 thousand, and 3.3 thousand. It's voltage divided by resistance because we covered up I. Applying Ohm's law to each one of these branches, we get 15 volts divided by 470 ohms, 32 milliamps. 15 volts divided by 2.2 thousand ohms, and we get 6.8 milliamps. And then lastly, 15 volts divided by 3.3 thousand ohms, and we get 4.5 milliamps. So let's look at the trend. As the resistance gets bigger and bigger and bigger, our current does the opposite. It gets smaller and smaller and smaller. Now that makes sense. If you're going to resist the flow of current with a bigger resistor, you're going to get less current. So this is kind of the opposite of what we saw with the series circuit. Bigger resistors had larger voltage drops. But here, bigger resistors are going to give us smaller current flow. Let's find out what the total current is. We're going to take 15 volts and divide it by the total resistance that we've already solved for. So 15 volts divided by 346.59 ohms, and we get 43 milliamps. So the question is, if we add up the current for all 3 of these branches, is it going to equal 43 milliamps? Because that's what Kirchhoff's current law, tells us. So we're going to add them all up, and what do we get? Well, 43.278 milliamps equals 43.278 milliamps. All right, they are equal. All right, Kirchhoff's going to be very happy. So can we combine these circuits? Can we have parallel and series together? Well, yeah, you can. You can have combination circuits, and that's what we have here. So we have light bulb 1, light bulb 2, light bulb 3. And as you look at this, examine it. What would happen if you removed light bulb number 1? What about light bulb number 2? Or light bulb number 3? What would be the consequences? Lastly, I want to talk about electrical power. I do talk about power in some of my other videos that involve simple machines. Power is measured in watts, and it's directly related to the amount of current and voltage within a system. So the power is equal to the current times the voltage. You increase the current or you increase the voltage, you get more power. All right, thank you very much for watching Robot Readinger, production of Introduction to Electricity, Part 2.